This is Computer Organization and Architecture class. And in Chapter 2, we will talk about the instructions. And that's the language of the computer. To revise what we've said in the last video about the instruction set architecture, the ISA. The ISA actually defines the set of machine instructions. So it's a group of instructions that a processor can fetch, decode, execute, access the memory, and finally write the result back to the memory. As you can see here in this sketch, the instruction set architecture is residing between the software layer and the hardware layer. The software layer includes the application, the algorithm, the code, whether it's high-level language or an assembly code. And in the hardware part, we have the processor, the memory, the data path, the control, and below that, the gates. And going deep, we have the transistors, and we end up with the physics. Different computers have different instruction sets with the possibility of having some similarities. However, if you have computer A, it has its own ISA. Computer P have also its own ISA. Now, computer B ISA won't work on computer A, and vice versa. Early and many of the modern computer has simplified instruction sets or simplified ISA. Now, what we are going to study in this class is the MIPS instruction set. It's now a company called MIPS Technology. This is their website, and it was originated from Stanford University. It's targeting a large share of the embedded core market. It has different applications in consumer electronics, network, storage equipment, cameras, printers, etc. And MIPS is actually typical of many of the modern ISAs, and that is implemented for many of new microprocessors. Now, this is the MIPS ISA summarized on those three tables. We will look quickly at the component of the tables, but by the end of this set of slides, you should be able to understand every row in these three tables. So the first is the MIPS operand. We have 32 different registers, as you can see listed here, and we have 2 to the power of 30 memory words, beginning from memory word at location 0 up to this location. Now, we have those 32 registers listed here from register number 0 all the way to register number 31, and everyone has its own purpose as it's stated here in this column. Now, the MIPS assembly language, which is the core of the ISA or the core of the MIPS ISA, are categorized in those different categories. The first one is the arithmetic, meaning how to add, how to subtract, and how to do the arithmetic operation using assembly language. You can see that we have the instruction here. This is an example how to write it in the assembly code. And this is the meaning. What does this instruction means? And here are some comments sometimes to make things clear. Of course, each one of them, we will study them in details in the coming slides. We also have data transfer functions or data transfer instructions. They are mainly the load instruction and the store instruction. The load, you are loading the variable from the memory, meaning that you are reading it, or you store the value to the memory, which means that you are going to write to the memory and save the value. It has different versions, as you can see here. The logical category, the logical instruction, mainly and, or, nor, and shift instructions. We have the conditional branch, which is actually the equivalent of the if statement. When there's an if statement in the high-level language with a condition, the equivalent to that in the assembly, it's called branch. Of course, the same thing could be said about the for loop, the while loop, and so on. We have also the set on less than, and this is if you have the comparison with less than or large than or less than or equal or large than or equal, those kind of conditions. And we have the simple versions, branch on equal, branch on not equal. And the last category is the unconditional jump. It doesn't have any sort of condition. It jumps right away to a certain position, and it has certain versions. I'll try to explain this a little bit more, this table. We have the 0 register that saves the value or the constant 0. We have those 3 rows. The first one is T0 to T7. They are temporary registers where you save temporary values there. If you have a method or a function, then the variables inside the functions are saved as temporary values. And you have also from T0 to T7, that's register number 8 to 15. And we have T8 and T9 a little bit away from them, starting from 24 to 25. It's actually only 2. We have also saved register from S0 to S7. That's from register 16 to 23. And you will find that most of the assembly languages, we use those registers. We have other registers. Some of them are pointers, some of them reserved for certain usage. And here, those 2, one of them, if you have a method, you have the arguments from A0 to A3, and you have the returned values from V0 to V1. Now, we will start by building up to the assembly language step by step. So as arithmetic operations, it's the add and subtract. We use 3 operands. 2 of them are sources and 1 destination. If we write it this way, add A, comma, B, comma, C, this means that you add B plus C, you get the result, and then you save it into A. As you can see in the comment part here, the comments in the assembly language start with hashtag. After that, you have the comment. Some people like to say sharp. It also works. All arithmetic operations have this form. Actually, many of the assembly instructions have a very similar form to this one. Now, the first design principle that we are gonna employ in designing our ISA. Actually, this is MIPS ISA. So as we explain it, the first design principle is simplicity favor regularity. The regularity makes implementation simpler. Simplicity enable high performance machines at very low cost. And don't forget the 8 main ideas that we've discussed in the last video. That's the code, a C statement. It could be also a Java statement. If you say that F equals to G plus H minus I plus J, you know the order of operation, that we first get I plus J, get the result, G plus H, we get the result, and then we subtract this from that. To be clearer, we start from the left side. First, we get this one. Once we get the result, we calculate this one because it has parentheses. Once we get the result, now we subtract this entity from this entity, and we get the result into F. Now, in MIPS code, in MIPS assembly code, that it will have, instead of one statement in the high-level language, it's 3 different instructions in the assembly code. So what we do, we add G plus H to get this result, and then we get it, and we put the result in a temporary value, T0. Similarly, we add I plus J, and we give after we do the operation or the addition operation, we put the result into the temporary value, T1. Now, we take T0 and T1, and we subtract T0 from T1 using the subtract instruction, and we put the result into F. You can see that we used 2 different instructions. The first one is add. We use it 2 times, and after that, we use the subtract instruction. In MIPS, the syntax operation is add, and sub. You notice that it has the same 3 operand strategy. 2 of them are sources and 1 is destination. 2 sources, 1 destination. 2 sources and 1 destination. Now, this is a very simplified form of the MIPS assembly code. This is not the final. If you put this in an assembler, it will have a lot of errors. We will build up step by step until we get the final code. Now, it's good now to understand the 3 rows that I talked about in the registers. We have the registers from register 8 to 15, that's from T0 to T7. T8 and T9, that's register number 14 and 24 and 25. And the registers S0 up to S7, these are the register from 16 up to 23. As you can see here in the descriptions, the temporary registers are used usually inside a function or a method, and the S, when you care about the value being an input variable or an output, whether it's source or destination, you put it in a saved register. When you use temporary, it's temporary. So after a while, if you lose this value, it doesn't matter much. It's just a temporary value. You hold some variable on it, and then you can reuse it somewhere else. But the saved, if you care about the value, you keep them in the S registers, From now on, we will call these registers. So the arithmetic instruction use register operands. The MIPS have 32 registers. These are some of them, some of the 32 register. Each one of them is 32-bit. So T0 is 32-bit, S0 is 32-bit, S3 is 32-bit, and so on. We use those registers for frequently accessed data. It's numbered from 0 to 31. This is, you can access the register using its number, but sometimes it's difficult to remember which one is the register. So we use the name in the assembly code. We use the name. So the 32-bit data called a word. From now on, any 32-bit data, we will call it a word. This means 16-bit would be a half word, and 8-bit, we know that this is a byte. The assembler names, as you can see, from T0 to T9. So make sure you don't exceed that limit. You have up to T9. There is no T10. And you have from S0 to S7. This is for the temporary values, and this one for the saved values. Just as a rule of thumb, if you don't care about the data, you just want to save it temporary, use a temporary register. If you care about the variable, then use a saved register, meaning S0 to S7. Now, here is the design principle number 2. Smaller is faster. This is contrary to the main memory. In the main memory, you have millions of locations. But here we have only 32 different registers. Each one of them is 32-bit. So, for example, register T1 has 32-bit. Register S3, it has 32-bit. And that's it. The main memory would have a lot of location. Actually, the main memory in the MIPS is starting from location 0 all the way to location 2 to the power of 30 minus 1. Now, we're going back to our example. Now we will, instead of using variable names, G, H, I, J, and F, we will use registers. So you can see, now we have those 3 instructions, and now we use the temporary as a destination. So if we say that this one, the variable G is an S1, this is an alphabetical order, G, H, I, and J. So S1, or let's say that this is S, if the order is like this, F, G, H, I, and J, we will make this S0, S1, S2, S3, and S4, just to make it easy to remember. So what would happen here now in the assembly code, we will make the addition S1 plus S2 this way, S1 and S2. Notice that in the registers, we have to use $sign. This $sign means that the coming is a register. After the $sign, this is a register. So every register has a $sign in the name of the register. So you have $sign S1, $sign S2, but we are not going to mention this every time. We simply say S1 and S2, and you know that there is a $sign in there. So you have S1 plus S2, meaning G plus H, and you get the result and you put it in the destination T0. That's the value of this part. S3 and S4, that's I and J. You add them and you put them in the temporary value T1. Notice we use temporary values. Those are important to us because it keeps the original variables in the high-level language. So we kept them and we saved them in those registers. Now, if we want to use a temporary register that helps us in the calculation, because this is a long statement and we have the assembly only 3 operands, then you add those 2 and get it to the temporary result T0, and then those 2 and you get the result to T1, and after that you subtract T0 from T1 and you give the result in S0. After this, if you have another code, you could use T0 and T1 again. But if you want to use S1 or S2 or S3 or S4, this means that you will overwrite the original values. So you have to be careful. Now, the memory operands, the main memory used for composite data. It has array, structured dynamic data, and many things. To apply arithmetic operation, you need to get the variables from the memory, meaning that you want to read them. And this is what we mean by loading the values from the memory into registers. This means that you read from the memory, and now the value is in the registers that we can use in the assembly code. Or you store the results from the register to the memory. Now, the memory is byte address, meaning each byte identify an 8-bit byte. The words are aligned in memory. And now we use this word. The words means that each one of them is 32-bit. So this means since the memory have 8 bits, if you want a variable, then you need to contain it in a 32-bit location, which is 4 bytes, 4 of the 8 bits. You know that 4 times 8 is equal to 32. If we have 4 bytes, this means that we are having one word. Now, MIPS is big Indian. To understand this, any machine, either it's gonna be big Indian or little Indian. If you have this value, for example, 0x0, 1, 2, 3, 4, 5, and so on, up to 7. And you have the locations starting from 0x100, 0x101, 102, and 103. Similarly here, it's from 100 up to 103. Now, if you want to save this value and your system is big Indian, you start by taking, since the word big, this means that you will start from the most significant bit. So you start from here and take the first byte and you store it here. And then you set the second byte and you store it here. The third byte and you store it here. And the last byte and you store it here. That's the big Indian system. The little Indian, you start from the least significant byte, which is this one. So you store this first and followed by this, followed by this, and last you end up with this one. Now, MIPS use big Indian. So all the variables, all the instructions, if you are dealing with the memory, you are trying to access the memory, it is a big Indian system in MIPS IC, which means the most significant byte is located at the least address of the word. So you get the most and you put it in the least position, which is the 100, followed by the 101, and so on. That's contrary to the little Indian, as we explained. Now, we mentioned that we have a word. And when we say a word, then it's 32-bit. Now here, if we have this C code, where you have G is equal to H plus A of 8. Now we have an array. So the arrays starting, if we say that we have an array A, and we have A0, A1, A2, all the way up to A8, let's say, then each one of them, each one of these variables must be contained in 32-bit. In the memory, this is 1 byte, this is another byte, this is another byte, and this is another bit. So from byte 0 to byte 3, that's one word. Here we have 8 bits, 8 bits, 8 bits, followed by 8 bits. So the total is 32 bits. We do the same thing for all the variables. Now you can see that A0 start at location 0. A1 start at location 4. A2 start at location 8. So you know that every time we are multiplying by 4. So here we start at location 0 times 4, which is 0. 1 times 4, which is 4. 2 times 4, which is 8. So instead of drawing this every time, you know it from the index directly. If you have the index 6, so 6 times 4 is 24, and this is the beginning of your word. And with it will reserve 4 different bytes: 24, 25, 26, and 27. Here in this example, we have A8. So we know that A8, 8 times 4 is 32. So you start from 32, and you have to reserve 4 locations: 32, 33, 34, and 35. Now, to convert this C code to the assembly code or assembly instructions, first we have this assumption. This is S1, and H is S2. And for arrays, we should know where is the base address of the array. The base address of the array A, it's in S3. It's in S3. So S3 have the base address. The addressing mode in the maps, when you are dealing with memory, you have a base address, and you also have an offset or displacement. So if you know that the base address of A is at S3, if you want A0, you will add S3 to the number 0. If you want A4, you should add the base S3 to the number 16, and so on. Now, we know that index 8 of the array requires the offset 32, because 8 times 4 is 32, as we explained here. Why we are multiplying by 4? Because every 32-bit is actually 4 bytes. 4 bytes per word. So now how to do this? When we have a memory access instruction, we need to know the base register, which is in our case 32, S3. We need a base register, and we add to it the offset that we want. So now the load instructions, it has only 2 operands. The first one is the base plus the offset. And the second one is the destination register. Because this is a load instruction, you go to the memory, you found the base register, you add to S3 the offset 32, and then after that, you go to the memory to this address that we generated, the base plus the offset. We know that the address here is right here. So now we take the variable that was stored here. Let's say that the variable is 7,777. So this variable, now we take this data and we put it in the temporary register T0. This way we load. Now we load a word, and this is why we call it LW, load word. Now, after we executed this instruction, this means that we have the data correspond to this part of the statement. Now we need to add to that the data in H, which is an S2. So we add S2 with T0 that we already got here, and then we put the result in S1. One key information in this slide: in high-level language, usually you have only the index. When you go to assembly, you need two pieces of information. The first one, what is the base register? And the second one, after you know the index, you multiply the index by 4 to point to the same beginning location in the memory of the corresponding array member. So 8 times 4, we know it's 32, and we write down 32 here. The first piece of information is the base register. The second is what is the offset. To get the offset, you get the index and you multiply it by 4 and you plug it here. The syntax, of course, you can see it here. We have parentheses. The offset would be here, which is a number. It could be any number. It has to be a number, actually. And the other one here inside is a register. So it begins with a $sign. That's the memory operand example 1. We will go to the next one. Now we have the same thing in the left-hand side. Sorry, in the right-hand side. And now we are saving the result inside the memory location of the array member number indexed by 12. So now we have S2 here in H, and we know that the base register of A is S3. Now right away we calculate 8 times 4 is 32. 12 times 4 is 448. So we know the location in the memory for these array members. Now this two parts is similar to the previous slide. We had the load. After that we have the add, but in the add, after you add S2 and T0, we put the result in at the temporary value T0. Not that we reused the T0, that's fine. If you like to use T1, that's also fine. But here, since we use T0, we will continue using T0. Now, after this, you need to store the value right here. Again, remember, this is 32, and this is 48. Now, the displacement of this one, we already discussed it. It's written here. The displacement of this one is written right here, 48, and this is the base register. The base register, as long as you are accessing the same array, it's going to be the same base register. Now, the store word instruction stores the value that is in this register that you already calculated here, and you store it in the memory location indicated by the base register and the offset. So basically, in the load, you get the location. Once you get the base and the offset, you read from the memory into the register. In the store, same thing. You prepare the location by knowing the base and the offset, and then you take the value and store it inside the memory. Now, we will check the difference between the registers and the memory, since we talked about it. Simply, as you can see in this figure, the registers are smaller than the cache, and the cache is smaller than the main memory, which means that the main memory have a lot of location, probably millions. In the MIPS, we have only 32 registers. In the main memory, we have 2 to the power of 30 different locations, from 0 all the way to 2 to the power of 30 minus 1. Anyway, Comparing this speed-wise, it follows this arrow. So the registers is the fastest. The main memory is the slowest. Size-wise, the registers are very small numbers. It's limited, only 32. The main memory has a lot, millions actually. So the registers are faster to access than the memory. Operating on memory data requires load and stores. And we discussed the load word and the store word. More instruction to be executed. And we will talk more about the load and the stores in the coming slides. Compilers must use registers for variable as much as possible because they are fast and they are close to the CPU. Actually, they are part of the CPU. So only spill to memory for less frequent less frequently used variable. If you want to do some or have a assembly code that requires, let's say, 2 variables, you get those 2 variables or you read those 2 variables from the memory at the beginning. And you should do a lot of operation after that. And probably at the end, you save the result back to the memory. Register optimization is very important because there are 2 points here. The first point, there are limited number of registers. You have only 32. So make sure you use them wisely. Second, to the best of your capability, try to use registers all the time. Now we have immediate operands that have an immediate value in the instruction or a constant value in the instruction. So constant data specified in the instruction. For example, if we have an add instruction that adds the register S3 to the immediate value 4 and put the result in S3. Now this add instruction is called add I, meaning that it's an addition with an immediate value. That's the add immediate. There is no subtract immediate instruction, but we can implement it, this instruction, using other ways. But for now, there is no subtract immediate. Instead of having subtract immediate, we could implement it this way. You say add immediate, SI, and the immediate value minus 1. The immediate value minus 1. This means that the constant here is represented using 2's complement, where it has positive numbers, 0, and negative numbers. This leads us to design principle number 3. You should make the common case as fast as possible. Small constants are common to use, so put them as immediate values and use immediate operands, you could use the immediate instructions that have the immediate value to facilitate this. We said that we have positive and negative and 0. There is a special register called 0 register that has the constant 0. So whenever you want the value 0, it's already there in this register. So meaning, if you had this instruction, add S1 to 0 and put the result to T2, what you are doing here is you moved the value from S1 and you put it into T2, since you just add the 0. So now this is a good usage of the register S0 for moving instructions. Sometimes you need to move the variables from saved registers to temporary registers, work on them, and probably move the values back. To do this, you could use the add instruction with the register 0. Now here, since we have a register, another register, another register, then we are using the add instruction. If we use an immediate value like this one, 4 or -1, we use the add immediate instruction. Now, we have a quick discussion about the signed and unsigned number. Giving a 4-bit number. If we assume that the 4-bit number is unsigned, then the range is from 0 up to 2 to the power of 4 minus 1, which is from 0 to 15, indicated by this clock-like shape, from 0 up all the way to 15. 0 would be 0, 0, 0, 0, since we have 4-bit, and then followed by 1, 2, 3, 4. This is the binary representation for the numbers. This is 7. After that, we have 8, and so on, all the way to 15. In hexadecimal, the 10 would be A, 11 would be C, D, E, and F. If we assume that this 4-bit number is signed, now we have positive and negative. So our range is from -2 to the power of 4 minus 1 to positive 2 to the power of 4 minus 1, all subtracted from 1, which is the equivalent of this range for 4-bit from -8 to 7, and you can see them here. We have the 0 right here, and then we start the positive number this side, the negative numbers from this side. So this is +1, +2, 3, 4, 5, all the way to only positive 7. And from here we go to -1, -2, -3, -7, and also one more, which is -8. This is the 2's complement representation of the signed 4-bit number. In general, if you have an n-bit number and we want only integers, so no fractions here, x, this is an n-bit number, starting from bit xn -1 in the most significant bit, all the way to the least significant bit, x0. Each one of these bits should be multiplied to the power 2 of x location. So this one, x0 times 2 to the power of 0, plus x1 times 2 to the power of 1. Notice the index. Similarly here, all the way up to this most significant bit. Notice that since we have an n bit, we start from 0 to n minus 1. And the range, as we said, now we are generalizing. We took it for 4-bit in the previous slide, and now for an n-bit, we start from 0 up to 2 to the power of n minus 1. And this is an example. If we are using 32 bits, and this is the case in MIPS. In MIPS, all the data, as we've seen in the array A, are saved in 32 bits. So if we have this number in 32 bits, we know from the binary to decimal conversion that you studied in the digital logic design course, that this is going to be 11 in decimal. You can calculate it by only considering the bit position that have 1, which is this bit position, and this bit position. This is bit position that has the weight of 1, 2, this is 4, 8, and continue power of 2, 16, 32, 64, 128, 256, 512, 1024, and so on. So for this one, we add 1, 2, and 8, because we have 1 and 1 and 1 here, and the result is going to be 11 in this one. The range that you can represent here, if you are assuming unsigned binary integer, so the maximum number is this one for 32-bit, which is 2 to the power of 32 minus 1, which is this one. 4 billion something. Now, if you assume a 2's complement signed integer. So in the previous slide, these are unsigned binary integer. And this one are signed integers. And it's good to mention right now that for unsigned integer, we usually use the addresses in a memory. If you have an address, we start from address 0 and with positive addresses only. There is no negative address in the memory, for example. So if you are dealing with addresses, you should use unsigned integers. If you are dealing with numbers, variables, data that you want to add, subtract, work on them mathematically, you should consider signed integers. Now we have positive and negative, and the range that we have is from minus 2 to the power of n minus 1 to plus 2 to the power of n minus 1, and you subtract 1 from the positive side. So if you use 32, now you have from minus 2 billion, this is the least possible value in the negative side. And the most positive value is plus 2 billion something. So notice in the previous slide, it was from 0 to 4 billion. Now we break it into two, some parts for the negative, some parts for the positive, and we end up to 2 billion in the negative side, 2 billion in the positive side. Now, if you have a number, how to represent it? You represent it this way. The first bit, and only the first bit, which is the most significant bit, has a negative value. And the rest has positive value. As an example, if you have this number, that long number here in binary, 0, 0, 1, 1, and so on, to get the value of this number, this one would correspond to minus 1 times 2 to the power of 31. And then the rest are positive values. So this one, 2 to the power of 30. This one, 2 to the power of 29, and so on, all the way to the last 4 bits. This one is 0 times 2 to the power of 0, 2 to the 0 times 2 to the power of 1, and 1 times 2 to the power of 2. And this one would be, it's not written, but it would be 1 times 2 to the power of 3. You add all this together, and notice that you will have this number in negative, which correspond to this number. And the rest of them are positive. If you add them together, you will find them this way. And then if you do the operation, the mathematical operation, which is minus 2 billion plus 2 billion, but there are some differences here, as you can see. You see that if you subtract those, it would be minus 4. There is actually an easy way to get this, instead of doing it in using mathematical way. If you take the 2's complement, you start from the rightmost rightmost location in the binary digits. So you start from the right and go to the left. Look for the first one. So copy everything until you reach to the first one. Copy the 0, copy the 0, and then copy the first one. After that, flip everything. Notice there are all here all ones. So when you flip them, they will be zeros. All the way up to the end. And this value is equal to 4. If this is equal to 4, then this number is minus 4. And this is what we had here. This is how to calculate the 2's complement of any number. And we will see this in the coming slides. But first, we see the 2's complement signed integer. Bit 31st is the sign bit. If it is 1, then that number is negative. If it is 0, then this number is positive or 0. Minus 2 to the power of n minus 1, it cannot be represented. Meaning, if you have this number and you try to, this you could represent in the negative sign. But if you want the positive number for it, you don't have. So let me write it here clearly. Minus 2 to the power of n minus 1, it cannot be represented. And I'll give you a 4-bit example as a simple question. If we have n4, we have 4 bits, then 2 to the power of 4 minus 1, and we take the minus sign. You know that this is minus 2 to the power of 3, which is minus 8. So minus 8, which is equal to 8, this could not be represented in 4 bits. So it cannot be represented. But the minus 8 you can represent. So this number you can represent it. But if you want to get the 2's complement of it, you cannot represent it. To look at it in another example, the non-negative numbers has the same unsigned and the 2's complement representation. Here are some specific numbers. The 0 is all zeros in binary. All ones in binary, that's the minus 1. And to make sure, do the 2's complement. Start from the right and look for the first one. That's the first one. We copy it. And then flip the rest. You will notice that you flip everything to 0, which means that this number is 1 in this amount. So this number must be minus 1. The most negative value is when you have 1 in the most significant bit, which is the sign bit, the one that bit 31 that we said here. This indicates that this number is negative. Similarly here, though this one indicates that this is a minus number or negative number. So this is a negative number. The most negative number is this one. And the most positive number when you have a 0 here and everything here is 1, which is kind of the flip. This number flipped. All bits are flipped. Now the sign negation. How to get the 2's complement? To get the 2's complement, there is a property that you need to make sure of. If you have a variable x and you add x bar to it, meaning that you add it to its complement. So this complement is actually called the ones complement, where you flip all the bits. You will end up with minus 1, which is ones everywhere. Let's take a 4-bit example. If you have the number 5, the number 5 is this way in 4 bits. If you add this number, which is x now, to x bar, which is flip everything, the ones complement, and you add them together, you will end up always with ones, which is the minus 1. Now, since we are sure of this, we can say that we can take this one here on this side, and we take the x to the other side, which means if you have x bar plus 1, you will get minus 1. This is only, we did a mathematical equation manipulation. So we have x plus x bar equal to minus 1. Put this one here on this side and put the x on this side. So you will have x bar plus 1 and you will have on the other side minus x. So the negative value of any sign number is the ones complement plus 1. Or flip the number and then add 1 to it. To check an example, if you have the number plus 2 and 32-bit, it's 0, 1, and all zeros. This is plus 2. Or, sorry, positive 2. Now to get negative 2, you flip all the bits. You flip the 0 to 1, the 1 to 0, the 0 to 1, and so on. And then you add 1 to it. If you add 1 to this number, you will end up with 1 plus 1 is 0. Carry 1, and then the carry goes down, and you end up with this. Another easier way, if you have this positive number and you want to get the negative number, do the 2's complement. Starting from the right side, copy everything until you reach to the first one. So you copy the 0, and then you copy the 1, and after that you flip everything. And that's what we did here, and we reached to the same result. Now the sign extension. We should know the sign extension because in MIPS instruction set, we have, for example, the add immediate, it has a constant value, and the constant value, sometimes it's positive or negative. Now this immediate value, we will find that it's only 16-bit, and we will check this in more details. It's only 16-bit. If you want to get this 16-bit and then extend it to 32, or as the example suggested, if you have an 8-bit only and you want to extend it to 16-bit, the way to do it for sign number, if you have positive 2, then you repeat the sign. You repeat the sign. We know that the sign is 0, you repeat it all the way. If you have negative 2, meaning this number, then you extend this number to 16-bit by repeating the sign. So if you have 1, you repeat 1 this way. So that's the idea. If you want to do the sign extension, you replicate the sign bit to the left. Now, the hexadecimal is used in any binary system, especially when you are trying to get some addresses, memory addresses. It's good to write the address using hexadecimal form instead of a long binary form. So you should know that starting from 0, 1, 2, 3, 4, up to F. After 9, we use letters A, B, C, D, and E. The equivalent in binary is, as you can see here, this is 0, 1, 2, and 3, and so on. There is an easy way to fill this. You fill it by 0, 1, 0, 1, 0, 1, and so on. You repeat this process. After that, you have 0, 0, 1, 1, 0, 0, 1, 1, and so on. 0, 0, 1, 1, 0, 0, 1, 1. And the third position, or this is position 0, position 1, this is position number 2. Position number 2, 4 zeros followed by 4 ones, 4 zeros followed by 4 ones, and the next position, which is in this case the most significant, then you copy 8 zeros followed by 8 ones. So if, for example, we have this number in hexadecimal, now this would be 1 byte followed by another byte followed by another byte and another byte. Notice that we have 4 bytes, which means that this is a 32-bit number, or this is a word, a single word. Now, if you want to convert it to binary, you know E, looking at the table, is 0, 1, 1, 1. C is 0, 0, 1, 1. A is 0, 1, 0, 1. 8 is 0, 0, 0, 1. 6 is 0, 1, 1, 0. 4 is 0, 0, 1, 0. 2 is 0, 1, 0, 0. 0 is 0, 0, 0, 0. It's important to always remember. that if you are converting from hexadecimal to binary, you take 4 bits per hex digit. You have E, you convert it to 4 bits. You have 2, you also convert it to 4 bits. Now, representing an instruction, the instructions are encoded in binary. It's another name of it. After you do the encoding, it's called a machine code. The MIPS instruction encoded a 32-bit instruction word. And here's something nice. Everything is 32-bit in MIPS. If you are dealing with data variable, meaning you are adding X to Y and storing the result in another variable, those data is 32-bit or one word. When we talk about the data, same thing if we are talking about an instruction. So if you are, I'll just take an example from the previous slide, the first instruction that I fixed. This instruction is 32-bit. So I need 32-bit to have the machine code for this instruction. So we need to differentiate between the instruction and the data. Now here we have 2 data. Actually 3 data. We have this data, which is going to be 32-bit, having only zeros inside it. S1 have 32-bit, and T2 is 32-bit. Now this instruction, we write it in zeros and ones using also 32-bit. Now going back, small number of formats encoding operation codes, or what we call the up code, followed by register numbers, followed by many other fields. We need to organize this in a regular way to make remembering them easier. And when we design the hardware in future chapters, we will find that it will give us a huge advantage in terms of performance. Now, those registers on those 3 rows are the ones that we are using most of the time in the assembly code, as I said. And there are also other registers. We have register zeros, and we checked it. And we'll, in the coming of slide, we will mention those registers as well. So now we have different instructions. And we have 3 types of instruction formats. We have the R type, we have the I type, and the J type. The I type have the immediate value or the constant all the time here with 16 bits. The J type is the simplest format. It has only the opcode, and the rest is just an address that you want to jump to. The R type, there are many instructions that falls into this format or uses this format. It has number of fields, 6 fields. Remember them this way. It starts with 6 bits, ends with 6 bits, and the middle 5, 5, 5, and 5. Now for the I type, we take this into 2. It's like, just let me draw it nicely. If you divide all the formats into 2, the I type will take 16 bits and make it the constant or the address. Now we are enforcing the same thing that we just said before when we said that every instruction would be 32-bit instruction, meaning the length here is 32-bit, broken into, for R type, 6, 5, 5, 5, 5, and 6. So you see 5 and 5, this is 10 and 10, that's 20, plus 12 is 32. For the I type, as we said, we broke it into two. The constant or the immediate value, and this is why we call it I type, would be the 16-bit on the right, and we have three fields. Those fields are the same fields that you see here. We denote it with the same name to make things easier to remember and to make them regular. Now, for the J type, it has only one of them, which is the up. Now, this up, you see here, is the up code, meaning there is a code here that is 6-bit in every type that tells me exactly what is the instruction. Tells me what is the instruction. And we will see all the instruction with their respective up code in one of the following slides. Now, you can see here in the R type, we have the first source, RS, the second source, RT, and the destination. For the I type, we have a source and destination. Now we will check the content of the RS and RT and what exactly do they mean for every instructions, also in the coming of the slides. Up to this point, we just need to mention those two fields. We have a field here called the function field. You will see that the R type have a lot of different instructions that falls into this format. Those instruction has similar opcode. Let's say that the opcode is 0, 0, 0, 0, 0, 0, 6 zeros. Now, how to differentiate many instructions that have the same opcode? We use the functionality 6 bits at the end to differentiate between the different instructions. We also have the shift amount. The shift amount helps us when you have a shift instruction. When you have a shift instruction, and we will see this also in the coming slides. So now we know the R type has 6 fields, 6, 5, 5, 5, 5, 5, and 6 bits. The I type takes this half from the R type, and the rest is the immediate value. This is why we call it I type. And the J type, we have 6 bits, the opcode, and the rest is the address, which is 32 minus 6, which is 26 bits. Okay. Again, the up is the operation code. The RS is the first source register. The RT is the second source register. The RD is the destination register. The shift amount is indicating how many bits you are shifting. It's zeros if you don't want to shift. And for now, we will consider there are 5 zeros. The functionality is the function code, which is an extension of the up code. One of the examples that we took for the R format is the add instruction. And we call it actually R format because they use registers. So we don't use immediates. They are all registers. We call them R format. Now I write down this, or I copy this little table here just to remind you of the registers, which register and what is the number of the register. So register T0 is the 8th register of the 32 MIPS registers. So now we said when we wrote the instruction that this is a source, this is the source, you add them together and you put the result in the RD. Now, if you want to get the machine code of this instruction, the RD is here. You see that there is, it's like it's recorded in the machine code in an opposite place. So the RD would be here, and the RS and the RT would be here. So you copy the RS here, the RT is here, the RD is here, the shift amount is zeros for now, and the opcode with the functionality tells you that the instruction is add. This is in general, if you have an add with different registers. Now let's take a specific example. If RD is T0, RS is S1, and RT is S2, what happens now? The instruction is add. So we need to record the opcode as an R format. And we know that the functionality is add. And then we copy S1 here, register S1 here, register S2 here, register T0 is here, and the shift amount is 0. Now we need to find the machine code of this instruction. This means that we want only zeros and ones at the end. So what happens is, first, the R format, which is the opcode. We found what is the R format for the add. Also, we should find what is the functionality add as well. To get this, you reference this table. You can see that if your instruction is an R format, then you will have bits 26, 27, 28, 29, 30, and 31 bits this way. You have 3 bits in the row indicating 29, 30, and 31, and 3 bits in the column indicating from 26 to 28. So this means that the R format is 0, 0, 0. I take it from here. That's position number 26, 27, 28. And then 0, 0, 0. That's position 29, 30, and 31. That's the last position. So we have zeros in the R format. Now, if we have the R format, and notice here that we had it in bold, we have an extension table at the bottom for all the R formats. If you have the R format, meaning you have 6 zeros in the opcode from 26 to 31, then the functionality, which are the bits of the instruction, the bits in the least significant 6 positions from 0 to 5, they are like you see here. Now we know that we are using add. So look at the add inside here. Try to find the add and make sure that you use or find add. This is add. There is another instruction for the add immediate, and the add immediate, you'll find it here. We are looking for add. Now the add have the functionality field as 0, 0, 0, 0, 0, 1. So we go back and we put 0, 0, 0, 0, 0, 1 in the functionality, which is actually the value 32. And we have in the R format 0, 0, 0, 0, 0, 0. So we reference the table to find the opcode and to find also the functionality. Going back to the table, you can find all the categories here. You can find, for example, if you want to look for the load and the store, the load is here, the store is here, where they have other versions as well. You have the and immediate or immediate, all the kind of immediate instructions here. You have the jump and branch, the branches here. and you have a lot of R type. The add, the set less than, the shift left if it is logical, shift right logical, and many other functionality like the and, the or, the XOR, the not, and so on. Most of these instructions that you see in the table, we will come to them in detail. Now, going back, now for these registers, S1, S2, and T0, we just find its value from the table. The registers table. So T0 is 8, and we know 8 in binary is this way. Remember, this is 5 bits. This is 5 bits. S1 and S2, we know here that S0 is 16, so S1 must be 17, and S2 must be 18, and this is the corresponding binary representation for 17 and 18. And the shift amount, it's all zeros. Now we know that this is the machine code for this instruction. And this is what the assembler do. The assembler convert the assembly code to machine code. So basically, I write it in hexadecimal format below. So I took this 4-bit, and put it here. Those 4 bits here, followed by the other 4, followed by the other 4. The last 2 4 bits are this one and this one, here and here. So this is going to be 0, this is 2, this is 0, this is 4, this is 2, this is 3, and 2, and 0. So when you see this in a memory location, and you know that this is an instruction, you can do the opposite operation and find out that this is an add between S1 and S2. You add them together and you put it in T0. Of course, in the memory, they will look like this. Or if you want to use an hex editor tool, they will look like this. Now, this is the table that we just referred to, and we will refer to it many times for any opcode. Let me take an example of the AND and OR. The AND is going to be 0, 0, 1, 0, 0, 1. The OR is 1, 0, 1, 0, 0, 1. For the load and store, and this is very famous, and we will check them. The load is 1, 1, 0, 0, 0, 1. And the store is 1, 1, 0, 1, 0, 1. Also the jump and the branch equal. The branch equal is 0, 0, 1, 0, 0, 0. And the jump is 0, 1, 0, 0, 0, 0. These are different outputs that are, we use it many times, so it's good to mention them here. The logical operation. We use the logical operations when we want, for example, to shift left or shift right. If we want to shift left in C, in the C language, this is the bitwise operation when you want to shift to the left. This is when you want to shift to the right. This is indicating that this direction is the shift direction to the left, and this is the right direction. In the MIPS, the instruction is called SLL, meaning you are shifting left, and the shift type is logical. There is a logical shift, and there is also an arithmetic shift. The logical shift doesn't care about the sign, while the arithmetic cares about the sign. So the shift right is shift right logical. The bitwise and, or, and not is having those symbols in the C. And in MIPS, you do the bitwise AND using the AND instruction or the AND immediate, the OR using the OR MIPS instruction or the OR immediate. So these are the instructions that you are going to use for the AND, the OR. The NOT, we will use the NOR. We know that if you want to implement the NOT using the NOR, you could use the NOR this way, and you make both inputs the same inputs of the inverter. So use the NOR to implement the bitwise negation. Now the shift operation, we will start with this shift as we started here, and we will try to follow with the other instructions. The shift operation, it has R type, and we have SLL, which means you are shifting to the left logically. So shift left logical, shift to the left, and fill with 0 bits. So when you are shifting to the left, you will enter zeros as you shift. Shift right logical, same thing, but the direction to the right, and you also fill with 0. It's really important to know that when you shift to the left, you multiply by 2 to the power of I. So if you shift to the left by 1 bit, this means that you multiply by 2 to the power of 1. Let me rewrite it here. Shifting to the left by 1 bit is equivalent to multiplying by 2 to the power of 1. Shifting to the left by 2 bits, this is equivalent to multiplying by 2 to the power 2, which means this is multiplying by 2, and this one multiplying by 4. So if you want to multiply by the constant 4, shift the amount to the left by 2. Now, shifting to the right, you divide by 2 to the power of 5. Now, in the shift operation, we'll make use of the shift amount, and you will see this indicated by this example. If you have shift logical to the left, and you have this register, this is the source register, and we will use the RT. Notice that the RS is not used. The RS is going to be 0. And the shift amount is going to be, for this example, we make it 2. And we have the destination. After you do the shift by the amount, you put the result in RD. Similar thing, the RD is like in the opposite positions inside the machine code. The RD is going this way and the RT is going this way. The shift left logical is one of the confusing instructions, because you might think that since there is a number here, this is an I type. It's not an I type. It's an R type or R format instruction. Since you are shifting by only few digits, you can use the shift amount instead of using an immediate value that has 16 bits. This is why in SLL and SRL, we say that they are an R type or R format instructions. Things that you should remember too in the shift, the RS is 0. Now in this example, the shift amount is 2, so you copy 2. T1 goes here, T0 goes here. It's an R format, so the opcode is 6 zeros. Now, if you check the functionality of SLL, going back to the table, you will find that SLL is right here. Since it's an R type, you will look for the R type, and it's 0000, and you will find that this is the SRL, and the SLL should be in the table below, and you can see it here. This is the SLL, as you can see here. So the code for the shift is 000000. That's the functionality. The functionality bits from 0 to 5, the 6 bit in the right hand side of the instruction. So going back, we know that this one is code 0000. So we have 6 zeros here. The shift amount is 2. We copy 2. T0 is the register number 8. T1 must be 9. RS is always 0, so we make it 0. The R format is 0, we copy zeros. So this is going to be the machine code of the R-type format instruction SLL. Now, what happens in this instruction is, since you are shifting to the left by 2, this means that we take this value and we multiply it by 2 to the power of 2, which is 4. This 2 is this one. So you multiply T1 by 4 to get T0. This is very important when you are accessing an array. Let's say that you have A of I. To know the value that you should put in the offset, then you should take the value I and multiply it by 4. To do that, you could use this operation. Shift to the left logically, and you shift by 2 bit positions, which means that you multiply by 4. Now, you can check a lot of the R format instructions, and basically all the instructions, whether they are R type, I type, and J type. In your textbook, at the end, there is an appendix that lists all the instructions and how to use them. There are some example on them and some comments if certain instruction have special features. Now, the I type, as we said, we break the instruction, the 32-bit instruction, into 2, and this one would be the immediate value, and we have the opcode, the RS, and the RT. The immediate arithmetic, meaning add immediate, or immediate, and immediate, or the load and store. So we have the LW and the RW, the store, which is SW. We have LW and SW. This is for the load, and this one is for the store. The RT is going to be the destination or the source register number. So the RT, sometimes it's the destination, sometimes it's the source. For example, in the load instruction, the RT is a destination. In the store instruction, the RT is a source register. Now, this constant, since it's 16 bits, it's ranging from -2 to the power of 15 to +2 to the power of 15 minus 1. The address is an offset added to the base register. This offset is actually written here in the immediate value, and the base address is written in the RS. So the RS is always a source. The R type, the RT is sometimes a source, sometimes a destination. This is the design principle number 4. Good design demands good compromises. Different format complicate decoding, but allowing that all the instructions is 32 bits wide, this makes things simpler, easy to understand, and it gives us a lot of advantages performance-wise. So we keep the format as similar as possible. And you can see that we divided into 2. And this one we copied the same as the R type, the the left-hand side of the instruction. Now, this is the load and store examples. The load format is, or the syntax of the load instruction is load word. You have the RT as a destination. After you get the offset, the base register, and you add them together, you prepare the location, you get the data, and you put it here. And as you can see, it's indicated by this arrow. This is an example of the load where the base register is 2, and the offset is 20. This means in the high-level language code, it was A. If we say that the array is called A, then the index is 20 divided by 4, which is the index A5. So we take the A5, this 5 we multiply it by 4, it's 20, so we put the 20 here. This is the offset, and the base address is S2. If you add those two numbers together, notice that we are adding here. So we use an adder. So we add those together, and we generated the location exactly in the memory. And now we can get the data and store it into S0. So S0, you can see the cross here. So try to remember that the load and the store has a cross when you move from the instruction to the machine code. So this one here, from the syntax, we know that the 20 is the immediate value. We know that the S2 is the destination. Sorry, the S0 is the destination, and we put it here. The S2 is the source, and we put it here. So S2 will have the base register of the array. S0 will have the data. After you load from the memory or you read from the memory, you put it in this register, which is S0, and you need the opcode of the load. You go to the table and you found that the opcode is 110001, which is the decimal 35. We know that the S2, since S0 is 16, S2 must be 18, and S0, as we said, is 16. The 20 in binary is this way, 16 is this way, 18 is this way, and we got the machine code of the load word, which is this instruction. For the store, it has the same thing, the same format. You can see the example here. I copy it exactly here, and I just change the instruction from load to store. What happens here is the opposite instruction. So instead of here, we are reading from the memory, and we read from the memory into S0. Now here we have the value already in S0, and we want to get the location on the memory and save S0 from the register S0, the value that was in S0, we saved it from the register S0 and into the location in the memory, indicated by this gray arrow. But when you look at the instruction, the only difference, this 18 is the same 18, the 16 is the same 16, and the 20 is the same displacement, the same offset. The only change is the opcode. Here is 35, here is 43. In binary, The code for the load is 110001. The code for the store is 110101. And you can see that the difference between this instruction and this instruction is a single bit. This bit. So you see the power of ISA now. One bit tells you different story. That's a load, and this one would be a load if it is a 0, and if it is 1, it's going to be a store. Now, we looked at the immediate, the I type or the I format instructions, and now we will take more I type instructions. But before, here's the store program in the computer. When we say it's a stored program, it means that if you have a C code or a Java code with a lot of statements, we compiled those C code or this code into an assembly code. And the assembler compiled the assembler into a machine code and listed this code as zeros and ones into this part here in the memory. Now the memory should have two parts. One part have only instructions, and another part has only data. So the instruction represented in binary, just like the data. Instruction and data stores in the memory, but we will find in MIPS, it's having the memory, it has two separate memory, one memory for the instruction and another memory for the data. Meaning, in the instruction memory, it will have add, or, load, store, shift to the left, or shift to the right instructions. The data, it will have the variable themselves. So if we have an array, like array A, it would be stored in the data memory. The program can operate on programs, obviously. The compilers, linkers, assemblers, they work on the programs. The binary compatibility allows compiled programs to work on different computers. And this is why we have the high-level language in C and Java. You could work on them in any computer, no problem. But when you convert to assembly, the assembly works only on the machine itself that has a specific hardware. You can see it in the memory, it has a counting program. It has editor program, C compiler. Those are different programs. The payroll data, the book text, the source code in C. They are different applications. If, for example, in a Windows operating system, you opened 1, 2, 3, 4, 5, 6 different programs. Each one of them will have its own space in the memory. And inside this space, you will have only instructions. Instructions. And there is another part of the memory that has the related data. And there is an interaction between the processor and the memory. This interaction, we already talked about it, which is the load word and the store word. So you load, you keep loading the information, all the variables, work on them. Once you're done, you want to store something, you use the store instruction. Now, going back to continue the different operations, we have the AND operation. It's an R type, as you can see here. And if you have T1 and T2, and you want to AND T1 and T2, you do the AND operation, and then you store the result in T0. If T1 have this value, T2 has this value, and you AND them, you bitwise and or bitwise and every bit. So 0 ANDed with 0 is 0. Frankly, or in fact, every AND operation with 0 results in 0. This is why we have zeros here and all the way here, since one of the variable has zeros, or both. Only here we have ones in one variable. So 1 added with 1 is 1, and 1 added with 1 is 1, 0 added with 1 is 0, 0 added with 1 is 0. Now we'll take the same example with a different instruction, which is the OR operator or the OR instruction. Here, as long as you have 1 in one of the variable, the result is going to be 1. This is why we have 1 0 and the rest would be 0. Since we have 1 1 1 here, you copy it here because it's T1 or T2. If T1 have 1 or T2 have 1, then the result is going to be 1. And for more detail about the OR, you should revisit your digital design course. Now, the NOT operation is actually the inversion of all the bits. So if you have T1 and you want to invert it and store the value in T0, you flip everything. If you have a 0, you flip it to 1. If you have 1, you flip it to 0. But to implement this in assembly, we use NOR instruction. As I mentioned before, if you have the NOT is equivalent to the NOR, it's equivalent to the NOR, but with both inputs connected together. It's also equivalent to the NOR with one variable. If this is X, then this is X here. With the variable that you want to invert is entered as a first input, and the other input you have only 0. This works and this works. In our implementation, we use this. So what we did is we said NOR T1 with the register 0, and then we put the result in T0. This would work as well if we say NOR T0 T1 and we repeated T1, meaning that you are doing this implementation. However, we have a 0 register that has a constant 0, so it's good to use something that's already there. Now, one of the I-type instructions is the branch instruction. The branch is moving, you know that the codes execute statement or execute statements in sequence, one after the other statement. The first statement, the second statement, the third statement, and so on. Some statements control the flow of the program, meaning that it goes from this position and jumps somewhere else, or jump back. This happens in the if statement, the for statement, the while statements, the do while statements, the case, the switch case, the switch statement with cases, and so on. And it's implemented in assembly using many instructions. The famous ones are branch if equal, branch if not equal, and unconditional jump. In branch or equal, unequal, meaning that you compare two source registers, RS and RT. If they are equal, you jump to this location using this label, L1. Here, same operation, but now you compare if they are not equal. And then you jump to this label. In the jump, there is no condition that you look for. Directly jump to this label, and that's it. Now, the branch equal and branch not equal, they are I-type. This L1 will be the immediate value, and it has 16 bits. The R and S, the RS and RT, they are the two fields that you see here. And the opcode, there will be an opcode for the branch equal and there will be a different opcode for the branch not equal. And the same thing also for the jump. It has its own opcode. However, the main difference between these two and this one is this one is a J type that has only an opcode, and it has a 26 bits reserved for the label. And this gives us the following conclusion. The branch has limited jump, or let me say limited movement. So if you branch onward or branch forward or backward, you have up to 16 bits for the label. But for the jump, you have more range, because you can represent the L1 using this 26 bits. We'll see more detail about this and how it's managed in the assembly code. Now, starting with the branch, assuming that L1 is equal to 3. If we have this instruction, this is one of the simplest conversion from the assembly to machine, because S0 is right there, S1 is right there. Meaning this is the RS here, this is the RT here. It's very important to know branch equal or even the branch not equal, they don't have a destination. There is no destination here. You just read the source, the other source, compare them, either you branch or not. So S0 is 16. And this you can see here, S0 is 16. S1 is 17. And the branch equal opcode, you can look at the table and you found that it's 001, 000. For the branch not equal, it's the following opcode, 101000. Same thing here, 16 and 17, and the label is 3. The job that branch equal do, it compares those two. If they are equal, you jump to the label L1. Here, if they are not equal, you jump to L1. Let's take the branch equal again. If you are executing this instruction, and you know that S0 have the value 5, S1 have the value 7, obviously they are not equal. So what happens to the branch now? Since 5 doesn't equal to 7, there is no branch. You do not branch till 1. You continue right after the branch equal, and you continue the next instruction and so on. Now, for the jump exit, usually this is the last instruction in the code. Jump to the exit, and the exit, if we say that the exit is equal to 2000, so you write down 2000. The jump opcode is 2, and that's it. 2000 in binary this way, and this is the opcode 010000, which represents the jump. Now, it's very important to know how to work with branch not equal, branch of equal, branch not equal, and also the jump. The reason is because they control the flow of the program. They control the flow of the instructions. When you are listing an instruction, you execute instruction after an instruction at a sudden or at a certain instruction, a branch instruction. You will face a branch instruction, and this branch instruction will tells you go somewhere else. So you need to understand the flow, and this is why we go back to flowcharts. If you have this code, C code, you have F, and you have a condition. If the condition is true, we call this a true path, and you have a true path statement. Else, this is the false path statement. In flowchart, this is the start, here's the condition. If it is true, you execute the green true path. If it is not, then you execute the red false path. Once done, you go to the exit. So if you start here, if it is true or false, once you're done, you will continue right here. Now, this is an example. If I is equal j, make sure you remember this for the comparison. This is the equal comparison. If I is equal to j, then you calculate f equal to the addition, else calculate f equal to the subtraction. So this is going to be the true path, and this is going to be the false path. Up to this point, everything in the flowchart is easy. Everything will be easy, hopefully. But the thing is, now we would see how to convert this one to an assembly code in this slide. I took both cases where you have the condition I equal to j and the condition I not equal to j. And I assumed that f, g, h, I, j are S0, S1, S2, S3, and S4 respectively. Now, for this one, since, let me record them, the I and J is 3 and 4. So this is S3 and this is S4. So the true path will be executed if they are equal. But in assembly, we care about when are we branching. You can see that when you are calculating this, next, normally you will execute the next statement. But the question is, when are you branching out of the normal sequence to somewhere else? And that's the answer. You branch if the opposite happens. Compare this one to this one. If it's equal between the operands, then you branch if it is the opposite, if they are not equal. And this is why we will have the subtraction in the false path if S3 is not equal to S4. Now, let's look to the other side. If they are not equal, then you branch if they are equal. And that tells us how to write the code. You start the code this way. You would say, the first statement that you write is branch not equal. You look at this one, and you found that there is an equal sign in the code. Directly, you start with the opposite, branch not equal. So you branch if those two, which is S3 and S4, are not equal. Where do you branch? You branch to the else, which is the red one. The red one is the subtraction between G and H. G and H is actually S1 and S2. So S1, you subtract it from S2, and you put the result in S0. The other one is the addition. S1, S2, you add them, and you put it in S0. And I should mention again that the subtraction is implemented using other methodologies. So we have the add instruction, and we have the subtract also instruction. Now what happens? We know that we write branch not equal. If this is equal in the high level code, you put branch not equal. You take the two variables and you branch to the else. Before you go to the else, right now you're not sure where do you write down the else. Right after this, you would put the true path, which is the addition. You put the add. After the add, you're done with the true path. Maybe one statement, maybe one instruction, maybe more than one instruction. It depends on how many instructions in the true path. The last one, after the last instruction, you say jump to the exit. Jump after the false path, you get the exit here, so you jump to the exit. Now, after you write down this one, you know that right after this you have else. And you put the false path. Now, you would notice that this code, the high-level code, is converted to the assembly similar to this one. The only difference is the branch type. This is branch if not equal. This would be branch if equal, and the rest is the same. Here are 4 pieces that are important. The first one is what to use, the branch not equal here and branch equal here. Before that, you have the start label, this label. That's the first piece of information. The second piece of information, what is in the true path, which is here. You put it, the true path. Copy the true path, you copy the true path. Followed by jump to exit. Now you're done with the true path. The third piece of information is the wrong or the false path, which is else followed by the instruction in the else path. And the last piece is the exit label. Notice the usage of the labels. In the branch, we use the else. That is here. Once you're done with the true path, you use jump to the exit, which is here. So, if you have this example, now we have a while loop. While an array called save with index of I is equal to k, then increment the index I. If we say that the I is an S3 and k is an S5, and the array save has the base register S6. What happens in the flowchart? In the flowchart, you have a loop actually, as long as this is equal to this one. As long as there is an equal between those two, you do the true path, which is incrementing the I and going back to the loop. If it is wrong, false, then you jump outside the loop to the exit. That's the flowchart. Now, since we said that k is an S5, and this save array have an index I, so we take the offset from S3 and we add it to the base register of S6, and we put the result in a temporary value T0 here, and we compare those two. If it is true, then you do this one, which is increasing I that is in S3 by 1. So we add immediate S3 with 1, and we get the result and put it again in S3. And then we jump back to the loop. If this is not satisfied, you do the wrong path. It's important. Since this is an equal size, the equal relation between the two, then we are branching if the opposite happened, when they are not equal. Now, we need to prepare the array first. If you see a code like this, and there is an array member, you have array with certain index, first thing, prepare it, and then work on it. To prepare it, you do the following. 3 instructions, one after the other. Shift left to logical, add, and then load. Shift left, because you need to take I and multiply it by 4, as we said before. To multiply by 4, you shift left the variable I, which is in S3, by 2 to the left, since this is shift left logical, and you put the result somewhere. We choose to put it in T1. After that, you add the index that you already prepared, which is I multiplied by 4, you add T1 to the base register, which is S6. Now you have, after the addition, you put the result in T1. In T1, you have the base register and the offset indicated by the index I, which is in another register. You get the correct calculation and you put it in T1. Now you are ready to load the information from the location and you put it in another temporary variable. To load it, you use the load instruction. Take T1, you already calculate T1 here, you prepared it. And the offset is 0 because you already added the offset to the register. So no need to use another offset. And then load the data that was in this location in the memory and put it in T0. Notice that we used T0 and T1. You could have used T2, T1, and T0. But notice that T1 is not important for us. So we reused it again because here we multiplied by 4. Now it's ready there, multiplied by 4. The I is multiplied by 4. It's ready in T1. And then we add it to the base register. And now we have the base plus the offset added together. And we can use it in the load instruction and load everything, or load the data in T0. In conclusion, if you have an array with index I, use those 3 instructions. Shift left logical, followed by add, followed by load. Now, after you prepare this, now you can work with the flow of the flow chart. You can work with the branch. They are equal here, so we must use branch not equal. Between what and what? Between whatever in T0 that we already calculated here and K. We know K is an S5, we say, okay, S5. If they are not equal, you branch to exit, which is the wrong path. Sorry, the false path. Otherwise, you work with the true path, which is add immediate S3 plus 1, and you put it in S3 again, meaning that you're incrementing the value of I, and you jump where, let's go back. Notice, using the if statement, we don't jump backward. We always jump forward. So when you jump here, else, you go here. When you branch to else, you go right there. Right? The direction of the jump is this way. The direction of jump is going down. The exit is the same. You jump right here. But in loops, there is always a jump to the back. And this is indicated by jump loop. So you jump loop and you go to the beginning to start doing the loop again. And notice what happens here. In the C code, we have I, and then we always increment I to get the new index of the array, the data and the new index, and so on. It's happening this way since you are adding S3, 1, and getting the result to the same S3. Next time, you will work with the new S3 and shift it by 2, and then add it to the base register, and then load, compare, and check if you're going to branch to the exit or continue. You continue and so on until you finish the loop. So now we have blocks. A basic block is a sequence of instruction with no branches or no jumps that break it apart. So for example, if you are starting with this loop, you say here is a label called loop or start. And then there are a list of instructions that begin with this label, probably a branch instruction or something like this. And then other instruction that doesn't control the flow. This gray part is called a basic block. And then we end the basic block here because at this point we have probably a branch or jump somewhere. So the basic block is a sequence of instruction that is not interrupted by anything, any branch or any jump. There is no embedded branches and there is no branch targets there. So that's one of the compiler jobs. When a compiler trying to compile a high-level code, it tries to get the different blocks in the program to make the optimization better. Now, here is more conditional operations. We have the set less than. Before, when we talked about the branch, there was always equal or not equal. This is the ones that we worked on so far. But what if we have less than or equal, greater than or equal? What to do with this? So if we have these, we can make use of the set less than. Set less than instructions, it compares those two. If this statement is true, then we write 1 in the RD. If this statement is not true, we write 0 in the RD. And that's what's explained here. You set the result to 1, which means this here, if the condition is true. Otherwise, you set it to 0. So now you compare those two. RS, is it less than RT? If yes, then RD is equal to 1. If no, then RD is equal to 0. Also, there is another version of it where you use an immediate value. Instead of another register here, you have a constant. And the same operation again. If RS is less than this constant, then you do this. But since you are using an I type, here we have RT, while here we have RD. Okay. Now, the set less than is usually an instruction that happens right before the branch instruction. So here we said set less than if S1 is less than S2 and put the result in T0. So if S1 is less than S2, what happens? This is going to be 1 if this is true. And now here we say branch if not equal. So now we know this is 1. If they are not equal, and 1 is not equal to 0, at this point you branch to the label L. So the branch instruction design, why not having a branch larger than, branch less than, branch greater than, and so on, instead of having two different instructions, one to know the set less than condition, and the other one after that is the branch. The simple answer to this, to make the common case fast and to make a good design compromises, and this will help us later by designing a simpler hardware. Having many instructions that do the same thing, sometimes this is create a redundant instruction that will be difficult to implement in the hardware. Now, the signed versus unsigned number is very important in the set less than, since you are comparing if they are less than or not. So let's say that you have S0 and S1. S0 is all ones, S0 is all ones, and S1 is all zeros. If you choose to have set less than, and you compare between S0 and S1, if they are less than each other, you know that S0 is -1, and S1 is equal to 0. If it is signed numbers, and they are signed numbers now, if they are signed numbers, -1 is less than 0, which means this value is going to be true. So T0 will equal to 1. Oh, sorry, this is not 0. This is actually 1. So this is -1 and this is 1. Same thing, it's true. -1 is less than 1. So this is going to be true, which is T0 will equal to 1. But if you use another instruction, variation of set less than, is called set less than unsigned. This means that it considered S0 and S1 as unsigned number, which means that this is going to be 1, and this one is going to be a really huge number with a lot of ones, which is this number, 4 billion. So that's a very huge number. And you are testing if this is less than 1, and of course this is not the case, so it's not true, and T0 will equal to 0. This means when you work with the set less than, be aware if they are the numbers that you have are signed or not, or unsigned. If you want them to be signed, use set less than. If you are working with addresses and you know there is no negative signs, then you should use set less than unsigned. At this point, we will move to the procedure calling. We have a good number of instructions that we understand fully. And after this, we will go through the procedure calling, where we have a certain method that do a certain job. We will write the high-level language implementation of a certain job, and after that, we will convert it to assembly with a list of instructions. Also, we will analyze different instructions that do certain jobs, and it will help us understand the MIPS assembly language better. And this is going to be the subject of another video.